All right, so time for Advent of Code day 22. We can remove these from yesterday because we're done with them. Okay, cool. So day 22, let's get rolling. All right, where are we? There we go. Day 22. What do we got? Crab combat. This is what I'm here for. I'm just picturing that photo of a crab holding a knife. No, it's a lobster holding a knife. Never mind. Okay, this is brand new territory for us. So let's find out. It only takes a few hours of sailing the ocean on a raft for boredom to sink in. Fortunately, you brought a small deck of space cards. Okay, I don't know what space cards are, but they sound great. That was from last year, day 22. I don't think I did last year. Maybe I did a couple of last year and I fell off. No, that's the beauty of Advent of Code. You can always go back and do previous years if you want. Okay, you'd like to play a game of combat, and there's even an opponent available, a small crab that climbed aboard your raft before you left. Fortunately, it doesn't take long to teach the crab the rules. Before the game starts, split the cards so each player has their own deck, your puzzle input. Then the game consists of a series of rounds. Both players draw their top card, and the player with the higher valued card wins the round. The winner keeps both cards, placing them on the bottom of their own deck so that the winner's card is above the other card. If this causes a player to have all the cards, they win and the game ends. For example, considering the following: 9, 5, 2, 8. Yeah, okay. This arrangement means that player's one deck contains 5 cards with 9 on top and 1 on the bottom. Okay. Player's 2's deck also contains 5 cards with 5 and 10 on the bottom. The first round begins with both players drawing their the top card of their decks, 9 and 5. Player 1 has the higher card, so both cards move to the bottom of player 1's deck, such that 9 is above 5. Okay. In total, it takes 29 rounds before a player has all of the cards. I mean, this, like, I don't know if you can even, can you call this a game? Is this a game? Because the cards, I mean, there's no strategy, there's no playing. It's just the cards are in an order, and basically you're just, two sentient parts of a sorting algorithm. Fun. Okay, once the game ends, you can calculate the winning player's score. The bottom card in their deck is worth the value of the card multiplied by 1. The second from the bottom is worth the value of the card multiplied by 2, and so on. With 10 cards, the top card is worth the value of the card multiplied by 10. In this example, the winning player's score is 3 times 10. Okay, so once the game ends, the winning player's score is 306. Play the small crab in a game of combat using the 2 decks you just dealt. What is the winning player's score? Okay, well, this seems deceptively straightforward. Yesterday also seemed deceptively straightforward, and I don't know if we got lucky. I think we got lucky and just happened to pick the right way to go about solving it, and that's why it went pretty quickly. By pretty quickly, I think it was like 2 hours. It was like an hour. I don't know. It was a long time. And I'm hoping this will be also similarly quick because I actually have to jump at 3 for a call. So I might be continuing this after that. So player 1, player 2, this is the following starting decks. Okay, so this is going to be our input right here. And I imagine our input is going to look very similar to this. Input. And I mean, we can verify that by just clicking on the Your Puzzle Input link. Okay, so this is what it's going to look like. There we go, playing. And several more rounds pass. And then post-game results. Okay, once the game ends, you can calculate the winning player's score. We're going to do that. So once the game ends, winning player's score is 306. So this is what we want. We want 306, and these are the steps we're going to take to get there. Cool. So let's make our section for defining things, then testing things, and then running the thing to give us the answer. No fancy CS words here. the part that the computer looks at. Okay, cool. So this is our input. We're gonna need to parse this into basically 2 arrays. We're gonna have 2 arrays of cards. So let's copy this down here, and we'll just whoop. Cool. So that's good. That's what our input looks like, and we need to parse it. So we're gonna write parse input. It's amazing, just how similar a lot of the steps in a lot of these things are. We're always parsing input. I mean, that makes sense because I always give you input. There's a lot of recurring themes in Advent of code, which is kind of cool. So what is this? This is a method that takes a block of text like the one above. So we're going to be splitting this into 2 sections, and they seem to be just split by 2 new lines. So I mean, that's really all we need to do here. Text split to begin with, split by 2 new lines, and that's going to be player 1, player 2, or I guess this is going to be deck 1, deck 2, and then deck 1 and deck 2 are each going to these are each we're gonna want to remove the labels player 1, player 2. So let's do that, and we're gonna want to turn these into arrays. So let's map these. So this is going to be also just a block of text, and this is going to give us back deck 1, deck 2. Okay, so this is going to be, I guess, there's doing this. Why are we even doing this? Text split, and then map, and then we can say that equals that. Okay. Okay. Okay, so we're gonna map each one of these is gonna be text, and then so we're gonna have the player name, which we don't care about, and then we're going to have a series of cards, and that is going to equal to this text split. I guess we should call it not text, we should call it subtext. Okay, we're gonna split that on a new line, and then what we're gonna do is we're gonna just return the cards map, and we're gonna put that through parse float. Okay. So let's see if this even works. So let's call parse. Oh, we're gonna need our usual comrades in arms, log and assert. Assert equals require assert. Cool. And let's log parse, or let's log parse input, and let's see what we get. Okay, so that's 2. So 9, 2, 6, 3, 1, and then 5, 8, 4, 7, 10. Okay. Cool. Well, that went surprisingly well. So let's remove that. So that's parse input. Now we've got our decks, and now what we're going to want to do is we're going to want to keep going until one of the decks is empty and apply the rules. So play the game. And this is going to take decks, which is an array of decks. Oh, my internet's being a little wonky, so sorry if the stream's cutting out a bit. Okay, so we're gonna play a game. We're gonna have a function that says play game. It takes in decks. I mean, we could also take in deck 1, deck 2. In fact, we can destructure it to be deck 1, deck 2, just like that. And what we're gonna do is we're gonna say while we wanna do this loop, we wanna play these things in a loop until one of the decks is empty. So until d1 dot length 0 is. I don't know why I got used to this, but I got used to putting the constant in these on the left, or d2 dot length 0 is. So in I think the reason why I do that is because if I have a function that produces this answer, then I can just say like length of d2 or whatever, and that reads better to me, rather than if I did it the other way, that it would be length of, and I have to put parentheses because you have to evaluate this before this, and like, you know, is 0. So I think that's probably why I do that. Anyway, doesn't matter, is d2 length. So until one of these decks is empty, what we're gonna do is we're gonna basically just take the first element off of that, which is unshift, I think. So we're gonna say card1 equals d1 dot unshift, and card2 is d2 unshift. And this is a function. Okay, cool. And now I think what we do in the game is we compare them. Whoever has the highest card has those put back onto their deck. So if card 1 is greater than card 2, what we do is we deck 1 dot push, and we do card 1, card 2. So we put them in, and then we wanna sort these by value, and that's annoying because JavaScript's built-in sort is it will just sort them by natural value. So 10 would come before 2 because the first digit's a 1 anyway. So fortunately these are integers, so we can say sort using this method. So that's what we're going to do. We're going to say a minus b. I think that will do what we want it to do. And you know what we can do? We can say new cards equals, and then we can new other is d2. So this would be else d2 push new cards. I feel like this could be refactored as well, but you know what, let's just see if it works. And until 0, okay, and then when it is, we will move on to the second part of this, which is returning the decks. So then we'll return d1 and d2, and we'll look at them. Okay, so going to log, play game, and this is taking a while. So let's take off this until, let's just do this once. And, oh, you know what? We need to push them on in this order. So let's put it back and see if it does shift, or if it does change things a bit. It does not. It seems to be running a very long time. Okay, so I'm going to comment out that thing. We're going to run this one iteration and see what we get. So we get 92613. So this is totally not what we were expecting, because the input that we had was 92631 and then 58472. Do I have a typo here? Card 1, card 2, card 1, card 2. Card 1 is greater than card 2. New cards. Play game. Parse input. Oh, you know, I don't need to do those. So yeah, okay. So why is it adding? It's adding 5 and 5 to the end of D2. So let's take a look at what new cards is here. Log new cards. Okay, so it's 5 and 5. So let's log D1. Okay, and let's log D2. Whoops. So let's log card 1. That's super weird. Am I having a brain moment where it's just like, oh, what's array unshift? What is unshift? Unshift adds items to the beginning of array. It's shift, not unshift. I always get that screwed up. Okay. So let's see what we got here. Okay, so this one won, but it put them back in the wrong order. So we want to say B minus A because we want them in descending order. Okay, so now he gets the new player 1 gets the new cards added to his. Wow. All right. Cool. So now we've gotten all the way back to this. We've got player 1, player 2. And what do we care about at this point? We care about okay, so player 1 plays 9, player 1 wins, then this is what we get. So we get 2, 6, 3, 1, 9, 5, and yeah, okay, so that's fine. Okay. These are the results. Player 1's deck, player 2's deck. 3 to 10, 6, 8, 5, 9, 4, 7, 1. Okay, cool. Once the game ends, you can calculate the winning player's score. The bottom card in their deck is worth the value of the card multiplied by 1, and so on. Okay, so then what we want to do is we want to score, and this is the only thing we need to do is we want the winning hand, and we don't care whose it was. So at that point, we'll just return one deck. So if d1 dot length will return d1, otherwise we'll return d2. Okay, so this will give us, oh yeah, score. It's not a thing. So this just gives us the one thing. So we're going to have a function called score deck, and this is going to take in a deck, and that deck is just going to be a series of cards. And what we want to do is we want to roll up the value. So that would be 1 times 1, 7 times 2, 4 times 3, all the way up to the beginning. So we can do this, I guess, like so. For card index in deck by -1. Let's do that and see what log index card gives us. So we're going to score the deck. And so that gives us 6, 9. Wait, what do we want? Play game. So we want to start with, we want 3. So log play game gives us that, and well, hold on, what we want to log, yeah, so what we're expecting here to log is the index and the card. So we want to see 1 first, I think. And score deck. Oops. And we do not. So we're seeing index 6, 9. That's just, oh, here we go, 9, and it was off the screen. So we're seeing 9, 1. So it's actually doing it in the reverse order, which I'm okay with, because it doesn't really matter for our purposes. Basically what we're doing is we're getting an index of 9 for the first one, and that's because it's going through it in frontwards order, but with a descending index. So that's and that's fine for our purposes, because that's all we really care. So what we want is we want index plus 1 times card. So this is going to be, 10 times the score of the first element, all the way down to 1 times the score of the last element. And what we're really going to do is we're going to have a rolling sum, and let's call this ret for the return value. We're just going to say ret plus equals index plus 1 times card, and then we're going to pass back ret is where we're going to go. So score deck gives us 299, which is probably the wrong answer. It should be 306. So 3 times 10. Let's log these. So let's say log that times that. Boop. So, oh, you know what? It's not actually iterating over the right way. So this needs to be. Once the game ends, you can calculate the winning score. Bottom card in their deck is worth the bottom card of their deck is worth the value of the card multiplied by 1, and the bottom card in their deck. So this is the top card. Let's see if that works. No. Oh, okay. So yeah, I was hoping this would actually just reverse it, but it doesn't. Okay. Well, what we can do is we can just call deck sort, or reverse rather, and we'll do that. Actually, we can just do that, and we don't need to buy -1. We should spell it correctly. Okay, so that gives us 306. We don't need this logging thing. We can do that here. And I mean, we could also technically reduce this. So this could also be deck reverse dot reduce, and then we take memo equals 0, and then the value, another card, and I think the third one is the index. So let's try that and just say memo plus equals card times index plus 1, and then we start that. We see that with 0. So let's see if this gives us the same answer. 306 it does. So this is the other way we could do it, and I don't really see this as being more readable. I think we talked about this briefly yesterday. This is basically the same thing, and I'm happy with it. Anyway, so what do we want to do? We want to log, so we want to assert that 306 is that, and then we want to log whatever we require input, and we're going to need the input, your puzzle input. Cool. Player 1, player 2. New file, input.coffee, and module.exports equals, cool. And let's see what this gives us. It's 3780. So let's try that. That's the right answer. Cool. We're 1 gold star closer to saving your vacation. Nice. Continue to part 2. You lost to the small crab. You know, I'm okay with that. I feel like the small crab, he deserves a win. So I'm just getting yeah. All right. Cool. So let's look at part 2. I got this copied into my paste buffer, and now we can see what they're going to do to us here. You lost the small crab. Unfortunately, crabs aren't very good at recursion. It's a bold statement. Okay. To defend your honor as a raft captain, you challenge the small game to a game of recursive combat. Recursive combat still starts by splitting the cards into 2 decks. Okay. That's only fair. Then the game consists of a series of rounds with a few changes. I guess the crab was player 2. That makes sense. Okay. Before either player deals a card, if there was a previous round in the game that had exactly the same cards in the same order in the same player's decks, the game instantly ends with a win for player 1. Before either player deals a card. Deals a card. If there was a round, a previous round in this game. So I guess they mean plays a card for before every round. If there was a previous round with the same cards in the same order. The game instantly ends with a win for player 1. Previous rounds from other games are not considered. This prevents infinite games of recursive combat. Otherwise, this round's cards must be in a new configuration. The players begin the round by each drawing the top card of their deck. Okay, if both players have at least as many cards remaining in their deck as the value of the card they just drew, the winner of the round is determined by playing a new game of recursive combat. See below. Okay, what time is it? It's 2:08. Okay. Otherwise, at least one player must not have enough cards left in their deck to recurse. The winner of the round is the player with the higher value card. Okay, as in regular combat, the winner of the round, even if they won the round by winning the subgame, takes the 2 cards dealt at the beginning, places them on the bottom of their own deck, again so that the winner's card is above the other card. Note that the winner's card might be the lower valued of the 2 cards. Okay, if they won the round due to winning a subgame, so it might be a lower valued card if they won the round due to winning a subgame. If collecting cards by winning the round causes a player to have all the cards, they win, and the game ends. Here's an example of a small game that would loop forever without the infinite game prevention rule. Okay, 43-19. Yeah, because the player 2 has more cards. And then, okay, during a round of recursive combat, if both players have at least as many cards in their decks as the number of the card they just dealt, the winner of the round is determined by recursing into a subgame. So, for example, if player 1 draws the 3 card, and player 2 draws the 7 card, this would occur if player 1 has at least 3 cards left and player 2 has at least 7 cards left, not counting the 3 and the 7 cards we've drawn. So to play a... Jesus, these rules are extremely complicated. Okay, so to play a sub-game of recursive combat, each player creates a new deck by making a copy of the next cards in their deck. The quantity of cards copied is equal to the number on the card they drew to trigger the subgame. During this subgame, the game is triggered. It is on hold and completely unaffected, so no cards are removed from players' decks to form the subgame. For example, if player 1 drew the 3. Okay, we're going to have to look at the examples here. And that's why you need at least that many cards in your deck, because you need to make a subgame out of those cards using the number of cards in your... Yeah, okay, so here's a complete example of game where game 1 is the primary game of recursive combat. Okay. Okay, so player 1 plays 4, player 2 plays 3, and... Okay, in this case, they both have 4. Okay, where's the too high? If there before anyone deals a card, if there was a previous round in this game that had exactly the same cards in the same order than the same and in the same player's decks, that had exactly the same cards in the same order in the same player's decks, the game instantly ends with a win for player 1. The game instantly ends. If there was a previous round in this game that had exactly... So if we enter a loop in a game, the game ends with a win for player 1. Okay. Jesus. Okay. You have 3 or 5. Okay, so after the game... Okay, let's look at these rules again. Now that we sort of know a bit more about what we kind of know a bit more about what we're doing. All right. So okay, we lost the small crab. Player 1, player 3. Okay. So these are the decks. They play as normal. 9 to 5, you get both of those cards. And then one of these rules is, otherwise this round's cards must be in a new configuration. The players begin the round by each drawing the top card. Off their deck as normal, if both players have at least as many cards remaining in their deck as the value of the card they just drew. If both players have at least, then they go recursive. So in that case, player 1 took a 4 and had 4 left, and player 2 played a 3 and had 4 left. So they both have, so the cards they drew are lower than or equal to the deck length, so they can play a recursive game, and so they must. Okay, otherwise at least one player must not have enough cards left in their deck to recurse, and the winner of the round is the player with the higher value card. Okay, all right. That's not, I think, you know what, I think it's not so bad. So let's make day 2. Day or 2 lit coffee. So I think I kind of have an idea of what they're doing. We're gonna keep this input, and we're gonna remove all this text, and we're gonna replace it with this new text. Part 2. Okay. All right, so let's, did I just overwrite my, no, here's my input. This is the previous input. I'm just gonna put it where they talked about previous, offer to play with the same starting decks you had before, and this is the previous input. Okay, so playing a small game that would loop forever. We don't want to simulate that. And then we'll throw in their example game. Okay, and I think that's basically similar to what they had here. Okay, cool. So what do we got? We still got parse input. We still have play game, but the rules have changed. And we still have score deck. So score deck is going to remain ineffective. Play game is now going to be slightly different. So we need to encode these rules. This was our previous rule, which is card 2 is card 1 bigger than card 2, then player 1 wins. So, and this is a round that we're playing. Okay, so this is also going to change. This is the new card, like how the new cards are sorted is going to change. So let's do that. Let's not sort them. In fact, we didn't need to sort them in the first place. We could have sorted them manually here. In fact, let's see if that works. 307. Oh man, I should have checked before. There we go. 307. Yeah, 3780. Okay, so whoops. Come on. Oh man. All right. So card 1, card 2. And this could be card 2, card 1. In fact, you know what? I like that. So let's backport that. Let's backport it to day 1. And this card 1, card 2. Cool. All right. So this is the simple case. This is the simple case, the old case. But we also have a couple new rules. We have before the card is drawn, we got a rule. So before either player deals a card, if there was a previous round in this game that had exactly the same cards in the same order in the player's decks, the game instantly ends with a win for player 1. So that's have we seen this state before? Have we seen this state before? If so, player 1 wins. And that's an instant win for player 1. So we want to return deck 1 at that point. Return deck 1. And cards are never created or destroyed. They're only moved from place to place. So really what we can do is we can just keep a running, you can see like an array of scene things, and we can either do the array, like put the array in there, so, or we can just like, we can basically just keep it as a key. It's gonna be sort of our cache that we're passing in. So if, and this is only in this game, before either, if there was a previous round in this game, okay, so this is gonna be instantiated every game. So if d1.join dash, sure, comma, excuse me, in scene, return d1. So this is gonna return deck 1 if oops, player 1 wins. So player 1, if we've seen this state before, player 1 wins. Okay, so that's player 1 winning. Otherwise, this is us dealing the cards. Deal the cards. Okay, otherwise this card's okay. Must be in a new configuration. The players begin the round. Okay. Cool. Then we have this weird step here, and this is the recursive step. So if card 1, I guess if card 1 is less than or equal to deck 1 length and card 2 is less than or equal to deck 2 length, so should we recurse? Then we need to figure out who the winner is, and so this is only returning a deck. It's not returning both. So I think what we should do at this point is we should return deck 1 and deck 2, and that's going to change. So this is going to give us 2 decks, and deck equals, we're basically going to take this logic out of here and put in the score, right? Here, okay, so this is going to be decks, and deck equals, otherwise, okay, if deck 1 length, deck 1 else. I guess we could sort them by length and just, I don't know, whatever. Deck equals deck 2. Okay, so let's see if this still works. Something's breaking. D1 is not defined. Oh, yeah, because this is going to be decks. So this is going to be deck 1, deck 2. Oops, all right. 3780. Okay, cool. So this is which deck are we scoring, and then yeah. In fact, we don't even care. We can be, because we can just do it for all decks, because the other deck's going to have a score of 0. So yeah, I mean, this is unnecessary. What we can do is we can just say for deck in. We could flatten them together, or we could just score everything. Okay, and so that's easier. Okay, so we got deck 1, deck 2. Should we recurse? So yeah, in this case we want to results, so we can have result 1, result 2, and then this is going to be equal to play the game, deck 1, deck 2. But we don't want deck 1, deck 2. We want a copy of deck 1, deck 2, and we only want to copy it the number of times on the card. So we effectively want to slice. So new deck 1 equals deck 1 dot slice, and then we're going to go 0 up into, I guess I don't need to call slice. I can just do this up to but not equal to card 1. And then new deck 2, 2, 2, and then this is new. Okay, so and it's expecting these as an array. So there you go. Okay, so now if r1 dot length, so if player 1, if result 1. Then what we want to do is we want to deck 1 push card 1, card 2, because they're going to come back in that order, not necessarily like we're still pushing player 1's card first because that was the winning card. Else pushing deck 2, pushing card 2. So that's if, and then else we do the simple case of who wins. So we could probably refactor this because you can see we're doing similar stuff. We're always pushing card 1, card 2 for this. We are always pushing, we're just deciding who wins is the only thing that changes in these cases. And this is how we decide who wins in this case, and this is how we decide who wins in the other case, which is all this rigmarole up here. We create new decks, we play another game, and then whoever wins. So let's see if this works. So this is now no longer asserting 306. This should, you know what, get out of there. Let's log that. 291. Is that what they wanted? 291. Perfect. Okay, so let's try it out. 291. And let's log score deck play game. So this is going to take a bit longer apparently. Interesting. So am I stuck in a recursive loop? It certainly feels that way. I'm going to assume that yes, I'm stuck in a recursive loop. So let's round 12, round 14, round game 5. So this is 17 rounds. And they did give us that example that we promptly ignored up above about, here's an example of a small game that would loop forever without the infinite game prevention rule. So let's make sure our infinite game prevention rule is working. So let's make infinite input. And let's make sure that it ends. So let's play game, parse input, infinite input, and make sure that it ends. So LGO, how about log? Try that one. So okay, infinite game isn't ending. So that means that our break condition up here, player 1 wins if we've seen this state before. Oh, because we're never adding it. Okay, So otherwise, we're gonna just scene dot push d1 dot join. So let's make this can equal to round key. Round key equals whoop. And then we can say return d1 if round key and scene, otherwise scene push round key. Okay, so now it ends, and now this should end. 34,107. Let's see if it ends. 34,107. That's not the right answer. Your answer is too low. Okay, so interesting. So let's 34,107. What's our input? Okay, so I mean it was playing for a while, so that's good. So log play game parse input infinite input. So I feel like let's make sure. Well, we know that it is jumping out here. Cool. So deal the cards, doing D1 shift, D2 shift. That's fine. Should we recurse? So we are recursing. So let's log that we're recursing. Log. How about log with 1G? Recursing. Okay, so we recurse a bunch of times, and then 4319. What do they say about who should be winning? Return to. Your answer is too low with whatever that was. 34,000. Okay. Return to day 22. Come on. So so player 1 in 4319 is what we're getting back immediately, even though because recursing was probably happening in this first one. Recursing is never happening in this one. But 291 is still coming back, which is interesting. So like, is there any recursing? Yeah, there is recursing in this, and that is working. Okay. So I feel like winning player's score is calculated from the cards they have in their original deck using the same rules as regular combat. Okay. Defend your honor. What is the winning player's score? So I feel like this should work, but it's clearly it's not, because it's giving us this number that's not true. So why is that? Is it recursing at the wrong time? So maybe let's check the rules. Let's do what we should be doing every time we run into a problem, which is reading the rules again. Okay, so before either player deals a card, if there was a previous round in this game that had exactly the same cards, the game instantly ends with a win for player 1. Is that what we're doing? Okay, so round key, and we just look to see if we've seen player 1's deck before. But that might not be the case. Hold on. If there was a previous round in which the game had exactly the same cards in the same order in the same player's decks. So you know what? This isn't making any assertions about player 2's deck. So let's do that and see if that changes things a bit. So let's just make a bigger key that includes player 2's deck. 2. So we're gonna make these, there we go. So that's our new round key. And this goes on further, apparently. Join. Here. Oh god. 34,107. I think that's pretty much what we had before. So let's log round key and just make sure that Okay, we're getting a lot of these, and so it's these to those, that to that, that to that. Okay, so that's very weird. But these are the sub rounds that are being played. Okay. So turn D1 if round key and scene, and it's playing a lot of rounds. So here we go. We start with these, and then it starts playing with a sub round. And we know that is being played correctly. So game 1, and then it becomes game 2 with 9852 1017. Yeah. Okay. And then after game 2 ends, it resumes round 10 of game 1 with 9852, 9852, and then this guy here, 634. Yep. Okay. So that appears to be working. So let's. So we found one problem, which is that we weren't really considering the states of both decks. We were really only considering the states of one deck. So where are the rules again? Previous rounds from other games are not considered. This prevents infinite games of recursive combat. Okay. Previous rounds from other games are not considered. Before either player deals a card, if there was a previous round in this game that had exactly the same cards in the same order in the same player's decks, the game instantly ends with a win for player 1. And I assume they mean that in the sub game, right? So a recursive game would end immediately for that. Previous rounds from other games are not considered. Otherwise, this round's cards must be in a new configuration. So I wonder if what they want us to do is they want us to pass that identity map down into the other game, but that doesn't make any sense because you can never have a sub game with the same number of cards that you had in your outer game. So that doesn't make any sense. Okay, I think we're probably okay there. So otherwise, what do we got? Otherwise, this round's cards must be in a new configuration. The players begin the round by each drawing the top card of the deck. Okay? If both players have at least as many cards remaining in their deck as the value of the card they just drew, the winner of the round is determined by playing a new game of recursive combat. See below. Okay, so we're going to have to check those rules out again. Otherwise, at least one player must not have enough cards left in their deck to recurse, and the winner of the round is the player with the higher value card. Okay. Cool. So where's okay, it said see below for the values of recursive combat. During a round of recursive combat, if both players have at least as many cards in their own decks as the number of the card they just dealt, the winner of the round is determined by recursing into a sub-game. Okay. To play a sub-game, each player creates a new deck by making a copy of the next cards in their deck. The quantity of the cards copied is equal to the number on the card they drew to trigger the sub-game. Okay. During this sub-game, the game that triggered it is on hold and completely unaffected. No cards are removed from the player's decks. Here's okay. A sub-game would be copies of the next 3 cards. Player 1 drew the 3 card. Their deck in the sub-game would be copies of the next 3 cards in there. And that's what we've been doing. That's what we've been seeing. So that's fine. After the game, the winning player's score is calculated from the cards they have left in their original deck using the same rules as regular combat. Defend your honor. So I feel like we did everything right. And yet we're getting the wrong answer. So that's super weird. 34107, and this is what we put in, right? 34107, and it's not the right answer. Your answer is too low. Yeah, I don't know. Now would be a great time if anyone's done this or anyone has any insights into what they think I'm doing wrong. Jump into the comments. There's a chat box that typically we use or I use for this exact kind of thing. If you want to give me a hint, I'd appreciate it. In the meantime, I'm just going to keep looking through the inputs to see if anything isn't making a whole lot of sense. So, I mean, like, there's no weird cases, like there's no zeros or anything in here. And we used the same input for the last time. So I feel like it's not the scoring that has changed, because the scoring still works. So if card 1 is less than or equal to deck length, deck 1 length, and card 2 is less than or equal to deck 2 length, then we have a subgame. And that slices the array, the deck, up to and not including the value of card 1. So we actually don't even need that. We can just do that and that. This shouldn't change anything. This is just removing some variables. And that doesn't change anything. It just removes variables. So if result 1, then do that. If result 2, do that. And then we return deck 1, deck 2, and we just score them all because it doesn't matter. And that's passing this assertion, and then we're just plugging in parse input, require input. Yeah, I don't know. I'm a little stumped as to why the answer is wrong. So this is the simple case. All we can do is we can go over the code and see if it matches with the rules. Simple case, higher card wins. Okay, so when the higher card wins, card 1 is greater than card 2, then you give it to D1, and if it's not, you give it to D2, and that means that card 2 is now the higher card. So here we go. So if maybe this is it. Do we always put it in? So do we always put it in? No, we put it in winning order, but this doesn't matter. This means card 2 could be smaller, but it could still be the winning card. It's still the winning card. So push card 1, card 2. But what if we reverse these? Would that still pass the assertion? It doesn't. Okay, so I know that's correct. And when we play a game, we're just playing it with the decks. Okay, and we've got this scene array, and we know that the scene array is working because it passed our infinite recursion test. And so this is a simple case. So this is, they both have that many cards, and we slice them out and we play a new game with them, and we get the results from the new game. Yeah, see, this makes sense to me. And we just, like, we're shifting off the arrays here, so we're mutating these arrays in place. And I mean, this is the same shit that we've been doing the whole time. Okay, so we're generating our round key. I mean, like, that could be the problem. Maybe our round key isn't correct. So 34107, yeah, we still get that. What about D2? I mean, this should be identical. 34107, none of this matters apparently. And if they're both combined together, then they're twice as unique. So our round key, I wonder, yeah, so this is gonna just cut out if the same state has been seen before. Okay, so returning deck 1 if Rankin scene. So because player 1 always wins. So we always, oh, we want to return, oh, this is weird. So this is actually not returning the correct thing. Oh, interesting. But we are testing if r1.length. Oh, interesting. Deck2. So this is always going to return just the state. It's going to return the state of the game. And so since we are, oh, this is interesting. So this is going to return, so you know what, we can't always assume that we're going to run out of cards. Sometimes that's what a return looks like. And this might give us a different answer, right? So the idea here is that player 1 wins, which means that they're going to be the only one with cards left. And since, oh, this is taking a long time. Oh, wow, it gave us a different answer. Okay, cool. So, and player 2 would lose, and effectively, since we don't want to count any cards that they had in their losing deck, then we can just truncate it, because the output of the games doesn't matter except for scoring purposes. Okay, so that's probably our issue right there. So 36, 621. So we can test this and see if that was the answer that they were looking for, and if it is, then that was our bug. And that's the right answer. Okay, cool. So that was the bug. Cool. And I'm gonna leave a note about this. So if player 1 wins, only their deck should be scored. So we truncate, or we remove the deck for player 2. And this would work in this case because we're always checking to see if player 1 has or the result 1 has a length. And that will happen either if we shortcut and they have a length and player 2 has nothing, or if they win and they get all the cards and player 2 has nothing. Otherwise, it will go to here. Okay, cool. So that's good. So that's day 2 in the bag. Got our assertion. It ran for a long time, but that was fun. Cool. So we still got the same parse input as before, and we still have the same, basically the same score deck as before. I think I updated it to just include all the decks, and I'm gonna backport that just because I think it's a better system than what I was doing here. So D2, and let's see if that still passes. It does, but it gives us a different. Wait, that wasn't, was that a different thing than the other thing? What was that? Index, nope, I'm in the wrong screen. So 3780, and let's check out, yeah, day 22, our answer, I think our first answer was 3780. Okay, perfect. All right, cool. So let's commit what we got. What are you doing? There we go. Is it that one? There you go. Let's commit what we got, and this is day 22 in the bag. Okay, and then we're going to readme. We'll add day 22 down here. And what was this called? It was called Crab Combat. What a great title. All right, here's this game that I always play, which is trying to guess how many spaces to add, and I lost. Cool, and I'm going to grab the ID, and we can paste that in here, and this is how to find this video later. And so we can now add day 22 to README. Cool. So thanks everyone who came along on my 22nd day of Advent of Code. Yeah, if you think maybe there was a way I could have done this better, would love to hear about it, either in the comments below, or if you're part of the Toronto.js Slack where we're hosting a channel, then you could also hear there. Otherwise, I'll see you guys tomorrow, same bat time, same bat channel, sometime after 1 because I sleep late, for day 23. All right.